Hello everybody, this is Scott Darmus here with an update on the perihelion precessions of the planets. In the last update I had calculated the perihelion precessions using the correct distances in the solar system. The semi-major axes are different in my theory because the equivalence principle is not correct according to my theory. So in the last calculation I used m here for Kepler's law, but the more precise version is using m plus 1, and the small mass is the planets are much smaller than the Sun, so the difference doesn't matter too much, but it does increase the precision quite a bit to use m plus m instead of just the big M. And something else I changed is I recalculated the relativistic precession. Before I just used the official values from Einstein's general relativity, but the semi-major axes are here as R, here represented as R, sometimes represented as L. So this doesn't make much of a difference, but a little bit. So before Mercury was at 99.97, now it's at 98. Actually, intermediarily it was at 99.999%, very high. But then I accounted for this relativistic part of the precession, and it dropped back down to 99.98%. Well, the standard deviations are quite significant, so that's fine. And here for Mercury, it was at 5.5 before I accounted for the relativistic corrections, the change in the relativistic corrections. So that was 99.85%, now it's 81%. And here for Earth, before accounting for the relativistic effect, it was it was still 93%. Actually, before I used the more correct semi-major axes with m plus 1, this was 99.98%. Now it's 99.93%. However, the biggest improvement here is with Mars. We see here that before it was 99.80%, now it's 99.88%. Before accounting for the change in the relativistic precession, it was 99.96%. That's quite an improvement. And then most significantly, I have calculated the anomalous precession of Jupiter and Saturn. And here I don't know the full precession, the measured value, only the anomaly, which there have been reports of anomalies with Saturn most famously, but also with Jupiter. And here the tricky part is that we don't know by how much the eccentricity of the orbit reduces the overall precession. But I had a look at the book of Fitzgerald, Patrick Fitzgerald, and he has listed some observed values, unsourced ones, but from there I basically took the reduction factor by how much it should be reduced. So here what I wrote down is not the full precession, but only the part that is unexplained by Einstein's general relativity. So here you see GR0 means it doesn't predict it, and here SPD minus 0.3. The observed one is 0.04, but we could argue that at the point when the Jupiter anomaly was reported, the models, the computer models, were already adjusted to some degree, so that the anomaly is partly removed. And so if we take this reconstructed value based on Jupiter, then it's an agreement of 45 plus minus 45%. Anyway, here we don't make any adjustments, so the reported anomaly is 0.92, and SPD predicts minus 3.1. So it's an agreement of 30% or 30 plus minus 9%. So these values are from computer simulations, and they're Newtonian. So it's a miracle that even any anomaly has been reported, because they get constantly adjusted away. Like the positions of the planets get readjusted all the time to make these anomalies go away. But this data here is objective. This is from Duncombe and here Newcomb. Duncombe didn't publish a value for Mars, so we have to take Newcomb. And so these are independent measurements, whereas the modern values are usually are not measured but derived from computer simulations. And yeah, that's all for now. Some important progress here. Okay, see you.